Hi, everybody. So here I'm going to talk through a very typical introductory circular motion question, and I'm going to talk through the forces at play and cover some common misconceptions about forces at play during circular motion. So our question is, an inelastic string is a light string is 3 meters long. It's attached at one end to a fixed point P on a horizontal smooth table. So this is our point P in the center of our circle and the other end to a particle of mass 2 kilograms. So here is our particle. If the particle is moving in a string with a constant speed 6 meters per second, okay, so our V is 6 meters per second, find the tension in the string, which remains taut and horizontal. Okay, so there's no slack in the string. Right. Now, to consider this problem, first of all, I'm going to look at this. So this is kind of a side-on view, bit of an angle, but let's look at it from a point of view of looking straight down from the top of this circle. So here this is an observer from the side, but here we're looking straight down from the top. So we have our radius of 3 meters. We have our particle, it's going around, and its velocity, so its constant velocity, its linear velocity is 6 meters per second. Okay, so that's our V. Now, let's consider here, first of all, things from the point of view of Newton's first law. So Newton's first law says that an object at rest remains at rest, or an object in motion remains in motion at constant speed and in a straight line. So here will be our straight line, our linear motion, unless acted on by an unbalanced force. So what Newton's first law is telling us is that for this particle, it wants to accelerate in this straight line at 6 meters per second, right? Tangentially in this straight line at 6 meters per second. Only if it's acted on by an unbalanced force is it going to continue in circular motion. Now, of course, our unbalanced force is our centripetal force. Our centripetal force is what causes our particle to continue moving in this circular way. And the difficulty sometimes is knowing the difference between the fact that the particle wants to continue. You know, if the string was cut at this exact moment, the particle would fly off in this tangential direction. And it's the same way if we think about not a string, but maybe gravity. If there was a switch that could turn gravity off, as something was in orbit at this point here, it would fly off at this linear motion. But that's a little bit more difficult to think about. So when we consider our particle here, even though we're only asked for the tension in the string, what's very natural here is to consider our forces up equals forces down. So our particle's on the table, you know, it's not going up or down, it's on our smooth table. So our forces up is equal to our forces down. Therefore, our weight, you know, 2g, which is a force down, of course. So our normal reaction is going to be equal to 2g. Forces up equals forces down. Now, when we consider the centripetal force, right, so the force that keeps our particle going around in a circle, we're going to say force centripetal is equal to mv squared over r. So that's our formula. What can be a little bit confusing is trying to think about this as perhaps equal balanced forces acting against each other in opposing directions. And you might be considering, well, I know centripetal force is acting towards the center, so centripetal forces are T, but what's acting against it? You know, what's acting against it? Well, the thing is here, there is no concept, there is no equivalent concept here of something like force in is equal to force out, because that's not the case. We don't have an equivalent outward force like this. It's the inward force that's keeping this particle rotating in a circle. Okay? And if there was no inward force here, then we'd have our linear tangential motion out to the side. So this can be the dangerous territory when we consider something like this, but it is the centripetal force that is our unbalanced force keeping our particle in its circular motion that it otherwise wouldn't want to be in. And then we can find, so the question was, let me keep this in order. The question was, find the tension in the string. So, our mass is 2 grams here. So we're going to have 2. Our linear acceleration was 6. So we're going to have 36 all over 3 like this. And we find our tension in our string, which is going to be 24 newtons. Thanks for watching.